Hello everybody, good morning. Myself, Dr. Shubhankar Sen from the Department of Mechanical Engineering, IIT ISM Dhanbad, welcome you to the fifth lecture of Module 7 of the 12-week SWAYAM NPTEL course, Finite Element Method in Thermal Engineering. In today's class, we shall determine the convection matrix using three-noded or quadratic bar elements, and next we shall derive the weak form as well as the semi-discrete form of the second order wave equation. As we have discussed previously, the second order wave equation, this is a hyperbolic partial differential equation characterizing a marching problem. So here we evaluate the entries of the convection matrix for a quadratic bar element. The convection matrix is defined as Cije equals to C into integration over omega e psi ie d psi je dx d omega e, where C equals to speed of the wave. This is a constant. So Cije we can represent in the natural coordinate as Cije equals to C into integration omega e cap to psi ie xi into d psi ie xi d xi into d xi dx d omega e. This is dx equals to determinant of je into d xi equals to dx d xi into d xi. We can directly substitute here as dx d xi into d xi. So this gives us C into integration from -1 to 1 psi ie xi d psi je xi d xi d xi. So this is je. So this portion becomes equal to 1. Now we draw a three-noded bar element with nodes 1, 2 and 3 in the natural coordinate system. We know that psi 1 e xi equals to minus xi by 2 plus xi square by 2. Psi 2 e xi equals to 1 minus xi square, and psi 3 e xi equals to xi by 2 plus xi square by 2. So this is a quadratic bar element in natural coordinates. So here xi equals to -1, xi equals to 0 and xi equals to 1. Now we consider I equals to 1 and j equals to 1 for a quadratic bar element. The convection matrix, this will be a 3 by 3 matrix. For a quadratic bar element, Ce equals to C11e, C12e, C13e, C21e, C22e, C23e, C31e, C32e, and finally C33e. So this is a 3 by 3 matrix. For I equals to 1 and j equals to 1, we get C11e equals to C integration -1 to 1 psi 1 is I d psi 1 e d xi d xi. So here d psi 1 e d xi, this is minus half plus xi equals to xi minus half. D psi 2e d xi equals to minus 2 xi and d psi 3e d xi equals to xi plus half. So here we get C11e equals to C into integration from minus 1 to 1. Psi 1 is xi equals to minus xi by 2 plus xi square by 2 into d psi 1e d xi. This is xi minus half. So this is xi minus half into d xi. This is equals to c by 4 integration minus 1 to 1. This is xi square minus xi into 2 xi minus 1 d xi equals to c by 4 integration minus 1 to 1 2 xi cube minus 2 xi square minus xi square plus xi d xi equals to c by 4 integration minus 1 to 1 2 xi cube minus 3 xi square plus xi d xi equals to c by 4 into 2 into xi to the power 4 by 4 minus 3 into xi cube by 3 plus xi square by 2 from minus 1 to 1 equals to c by 4 into 1 by 2 minus 1 plus half minus this is 1 by 2 plus 1 plus half. Here we get c by 4 into this will be equals to 0. So here we get half and half 1 plus 1 2. So we get here minus 2. So we get here minus c by 2. So C11e it comes as minus c by 2. Next we go for C12e. For I equals to 1 and j equals to 2, C12e equals to c into integration minus 1 to 1 psi 1e d psi 2e d xi equals to c integration minus 1 to 1. This is minus xi by 2 plus xi square by 2 into minus 2 xi d xi. This gives us C12e equals to c integration minus 1 to 1 xi square minus xi into xi d xi equals to c into integration minus 1 to 1 xi cube minus xi square d xi equals to c into xi to the power 4 by 4 minus xi cube by 3 from minus 1 to 1 equals to c into 1/4 minus 1/3 minus 1/4 plus 1/3 equals to c into 1/4 minus 1/3 minus 1/4 minus 1/3 equals to c into minus 2 by 3 equals to minus 2c by 3. For I equals to 1 and j equals to 3, we get C13e equals to c into integration from minus 1 to 1 psi 1e d psi 3e d xi equals to c into integration from minus 1 to 1 xi square minus xi by 2 into xi plus half d xi equals to c by 4 integration minus 1 to 1 xi square minus xi into 2 xi plus 1 d xi equals to C13e equals to c by 4 integration minus 1 to 1 2 xi cube minus 2 xi square plus xi square minus xi d xi equals to c by 4 integration minus 1 to 1 2 xi cube minus xi square minus xi d xi equals to c by 4 into 2 into xi to the power 4 by 4 minus xi cube by 3 minus xi square by 2 from minus 1 to 1 equals to c by 4 into half minus 1/3 minus half minus half plus 1/3 minus half. This is equal to c by 4 into half minus 1/3 minus half minus half minus 1/3 plus half equals to half minus half, they cancel out, plus half minus half, they cancel out. C by 4 into minus 2 by 3 equals to minus c by 6. So we have calculated the first row of the convection matrix for a quadratic bar element. Similarly, we can calculate the second and third rows of the matrix. So let us consider I equals to 2 and j equals to 1 gives c 21e equals to c into integration from minus 1 to 1 psi 2e d psi 1e d xi equals to c into integration minus 1 to 1 1 minus xi square into xi minus half d xi equals to c by 2 integration minus 1 to 1 1 minus xi square into 2 xi minus 1 d xi. This gives us c 21e equals to c by 2 integration minus 1 to 1 2 xi minus 2 xi cube minus 1 plus xi square d xi equals to c by 2 into 2 into xi square by 2 minus 2 into xi to the power 4 by 4 minus xi plus xi cube by 3 varying from minus 1 to 1 equals to c by 2 into 1 minus half minus 1 plus 1/3 minus half 1 minus half plus 1 minus 1/3 equals to c by 2 into minus half plus 1/3 minus 2 plus half plus 1/3. So this gives us c by 2 into minus half and half, they cancel out. So 1 by 3 plus 1 by 3 equals to 2 by 3 minus 2 equals to c by 2 into minus 4 by 3 equals to minus 2c by 3. Then for I equals to 2 and j equals to 2, we get c22e. For I equals to 2 and j equals to 2, we get C2 to E equals to integration from minus 1 to 1 psi 2E d psi 2E d xi equals to integration from minus 1 to 1 minus xi square into minus 2 xi d xi. Here c is outside, so we shall get from here minus 2c integration from minus 1 to 1 xi minus xi cube d xi equals to C2 to E equals to minus 2c into xi square by 2 minus xi to the power 4 by 4 from minus 1 to 1 equals to minus 2c into half minus 1/4 minus half minus 1/4. This gives us minus 2c into half minus 1/4 minus half plus 1/4 equals to 2c into 0 equals to 0. Finally, for the last term in the second row, we have for I equals to 2 and j equals to 3, C2 3e equals to c into integration from minus 1 to 1 psi 2e d psi 3e d xi equals to c into integration minus 1 to 1 minus xi square into xi plus half. This gives us c by 2 integration minus 1 to 1 minus xi square into 2 xi plus 1 d xi. This leads to C23e equals to c by 2 integration from minus 1 to 2 xi minus 2 xi cube plus 1 minus xi square d xi equals to c by 2. Then we have 2 into xi square by 2 minus 2 into xi to the power 4 by 4 plus xi minus xi cube by 3 from minus 1 to 1. This gives us c by 2 into 1 minus half plus 1 minus 1/3 minus, here we have 1 minus half minus 1 plus 1/3. This leads to c by 2 into 2 minus half minus 1/3 minus 1 plus half plus 1 minus 1/3. So here we get c by 2 into 2 minus 2/3 equals to c by 2 into 4 by 3 equals to 2c by 3. Here minus half and half, they cancel out. So it is 2 minus 2/3. Now for the third row, we have for I equals to 3, j equals to 1, we get C31e equals to c integration from minus 1 to 1 psi 3e d psi 1e d xi equals to c into integration from minus 1 to 1. We have psi 3e, this is xi square plus xi by 2, and d psi 1e d xi, it is xi minus half d xi equals to c by 4 integration from minus 1 to 1 xi square plus xi into 2 xi minus 1 d xi. This leads to C31e equals to c by 4 integration from minus 1 to 1 2 xi cube plus 2 xi square minus xi square minus xi d xi equals to c by 4 integration minus 1 to 1 2 xi cube plus xi square minus xi d xi equals to c by 4 into 2 xi to the power 4 by 4 plus xi cube by 3 minus xi square by 2 from minus 1 to 1. This gives us c by 4 into 1 by 2 plus 1/3 minus half minus half minus 1/3 minus half equals to c by 4 into 1/3 plus 1/3 equals to c by 4 into 2 by 3 equals to c by 6. For I equals to 3 and j equals to 2, we get c3 to e equals to c into integration from minus 1 to 1 psi 3e d psi 2e d xi equals to c into integration from minus 1 to 1 xi square plus xi by 2 into minus 2 xi equals to minus c integration from minus 1 to 1 into xi cube plus xi square d xi. It leads to c 3 to e equals to minus c into xi to the power 4 by 4 plus xi cube by 3 from minus 1 to 1 equals to minus c into 1/4 plus 1/3 minus 1/4 minus 1/3 equals to minus c into 1/4 plus 1/3 minus 1/4 plus 1/3 equals to minus 2c by 3. We are left with the last term of the diagonal in the third row. So for I equals to 3 and j equals to 3, c33e equals to c into integration from minus 1 to 1 psi 3e d psi 3e d xi equals to c into integration from minus 1 to 1 xi square plus xi by 2 into xi plus half d xi. So this gives us c33e equals to c by 4 integration from minus 1 to 1 xi square plus xi into 2 xi plus 1 d xi equals to c by 4 integration minus 1 to 1 2 xi cube plus 2 xi square plus xi d xi equals to c by 4 integration from minus 1 to 1 2 xi cube plus 3 xi square plus xi d xi equals to c by 4 into 2 into xi to the power 4 by 4 plus 3 into xi cube by 3 plus xi square by 2 from minus 1 by 1 equals to c by 4 into half plus 1 plus half minus half minus 1 plus half equals to c by 4 into 2 minus 0 equals to c by 2. So we have calculated all 9 terms of the convection matrix at the element level for the quadratic bar element. The convection matrix for the quadratic bar element is given by CE equals to C11E, C12E, C13E, C21E, C22E, C23E, C31E, C32E, C33E. We substitute the values here. So for the first row, our C11E, it was minus C by 2, and C12E was minus 2C by 3. So minus C by 2 and minus 2C by 3, minus C by 2 minus 2C by 3. Then we go for C13E. C13E, it was minus C by 6, minus C by 6. In the second row, we had minus 2C by 3, minus 2C by 3, C22E, C22E, it was 0, and C23E was 2C by 3, 0, 2C by 3. In the third row, we had C by 6 minus 2C by 3, C by 6 minus 2C by 3, and the last term C33E, it was C by 2. So this is a 3 by 3 matrix. So C12E here, this should be minus C, this should be minus C, minus C, minus C, minus C, here it is minus C, minus C, and ultimately it is plus 2C by 3. So here there is a correction. This C12E, this is 2C by 3. So here we have constructed the element level matrix for the convection term, and then if we look into this matrix, we see that we have a 0 in the main diagonal, and also the remaining terms of the diagonal, they are equal in value but opposite in sign. From here, we can predict that the assembled matrix using quadratic bar element will also become skew symmetric, the way we got skew symmetric matrices for the two noded bar elements. So the features of the element level convection matrix are: the matrix is asymmetric, the matrix contains a 0 in the diagonal, and the first and third terms along the diagonal are of same value but opposite sign. So let us check that the assembled matrix will be skew symmetric or not. For that, we shall consider only two quadratic finite elements. So let us consider two quadratic finite elements. So these elements we give numbering as element 1 element 2. Let us consider that the boundaries are of EBC type. So there we assign 0 equation numbers. So equation number 0, equation number 0, equation number 1, 2 and 3. So we shall have 3 unknowns, or the assembled matrix will be of 3 by 3 size. So the assembled convection matrix C, it will be C11, C12, C13, C21, C22, C23, C31, C32, C33. Now C11, this will be C221. Then when you go for C12, it will be C231. Then C13, it will be 0 because 1 and 3, they do not belong to the same element. Now we have C21. C21, it will be C321. Then C22, it will be C331 plus C112. Then C23, it will be C122. The last row C31, it will certainly be 0. Then C32, it will be C212, C212. And then C33, it will be C222. Now we can substitute the numbers here. We can see that C221, it is 0. C231, C23, this is 2C by 3. 2C by 3. Then we have 0. In the second row, we have C321. So C321 is minus 2C by 3, minus 2C by 3. Then we have C22. This is C331 plus C112. C331, this is C by 2. C112 is minus C by 2. Then C122. C122, this is 2C by 3. 2C by 3. Then in the last row, we have 0, the first term. Then C212. C212 is minus 2C by 3. Minus 2C by 3. And C33, this will be C222. C222, it is 0. So here we can finally get the assembled matrix as 0, 2C by 3, 0, minus 2C by 3, 0, 2C by 3, 0, minus 2C by 3, and here also we get 0. So we have seen that the property which we have seen for the two-noded or linear bar element, this is expectedly preserved for the three-noded or the quadratic bar element. So the quadratic bar elements also give a skew symmetric convection matrix. So we get skew symmetric convection matrix using the quadratic bar element. So we considered here, just we write more details. Consider two quadratic bar elements with EBC at the ends. So these are capital P or global equation numbers. So this is capital C is the assembled convection matrix. So we have shown that for quadratic bar elements also the assembled convection matrix is skew symmetric. So the proof is shown here. We separate this text. So now we shall derive the Galerkin weak form and the semi-discrete form of the second order wave equation. As all of us know that the second order wave equation, this is a classic example of the hyperbolic partial differential equation. The second order wave equation is given by del 2u del t2 equals to c square del 2u del x2, where c equals to speed of wave, u equals to u of x and t is the transported quantity or the DOF. So in this case, we ignore the source term. So we shall use the Galerkin FEM formulation. Use Galerkin FEM formulation. So if we notice in the transient heat conduction equation, in the first order wave equation, the time derivative was of first order. Also in the convection diffusion equation, in the Navier-Stokes equations of fluid motion as well as the energy equation, we have first time derivatives. But the second order wave equation is one of the equations in the thermofluids where we have the second derivative of time. So we use the statement of MWR to generate the weak form. It gives us integration over omega e w re uh d omega e equals to 0. So this problem we are dealing with in one dimension. We consider 1D case. So this gives us integration over omega e w into del 2u del t2 minus c square del 2uh del x2 dx equals to 0. This gives us integration over omega e w del 2u del t2 dx minus c square into integration over omega e w del 2u del x2 dx equals to 0. So use Green-Gauss theorem to evaluate the spatial derivative portion. This gives us integration over omega e w del 2u del t2 dx minus c square to minus integration over omega e gradient of w dot gradient of u dx plus boundary integral over gamma e w del u del n d gamma e equals to 0. We can simplify this expression as integration over omega e w del 2u del t2 dx plus c square integration over omega e dw dx into du dx minus c square integration over gamma e w del u del n d gamma e. So here this is the boundary integral term which we can consider as the NBC term. So if we consider the strong form, we can consider that both the EBC and NBC, they are defined for our case. So we use u equals to g along gamma g and c square del u del n equals to h bar on gamma h. So these are our boundary conditions associated with the weak form. The term c square del u del n or c square du dn, it represents our secondary variable. In 1D, n is equivalent to x. So this gives us integration over omega e w del 2u del t2 dx plus c square integration over omega e dw dx du dx equals to boundary integral over gamma e w into c square du dx d gamma e. So this is the weak form of the second order wave equation. Weak form of Galerkin type of second order wave equation. So we identify this weak form in a box. Now we shall find out the element level matrix equation. To this end, we shall first consider the trial solution and then we shall also use the Galerkin approximation. Consider the trial solution as u x t equals to summation uj psi j, where uj is a function of time and psi j is a function of space only, plus summation ube psi be x, where b belongs to eta g and j equals to 1 to nen. uje is a function of time. Use w equals to psi iex for Galerkin approximation. Substitute in the weak form to get, let us rewrite the weak form, integration over omega e w del 2u del t2 dx integration over omega e w del 2u del t2 dx plus integration over omega e c square dw dx du dx dx c square du dx dw dx dx equals to boundary integral along gamma e w c square du dx dx. We make the substitutions and then simplify. This gives us integration over omega e. W is psi I. We have del 2 del t2. For u, we can substitute summation of ujet psi jex plus summation of ube psi be, where b belongs to eta g and here we have j is 1 to nen dx plus c square integration over omega e d psi ie dx and d dx of summation uje psi j plus summation of ube psi be j equals to 1 to nen b belongs to eta g equals to boundary integral over gamma e psi ie c square du dx d gamma e. So we can simplify this expression as summation over j equals to 1 to nen integration over omega e psi ie psi je d omega e del 2 uje del t2 plus summation of b belongs to eta g integration over omega e psi ie psi be dx d omega e means dx. Here you can directly write dx into del 2 ube del t plus c square into summation over j equals to 1 to nen d psi ie dx d psi je dx dx. So here dx should come into uj plus c square summation over b belongs to eta g integration over omega e d psi ie dx d psi be dx dx multiplied with ube equals to boundary integral along gamma e psi ie c square du dx d gamma e. Now the nodal vector uj, it is only a function of time. Because of this, we shall write this equation as an ordinary differential equation. Since uj is a function of time only, the above equation is written as an ODE. So we can write it as summation j equals to 1 to nen integration over omega e psi ie psi je dx d2 uje dt2 plus summation over b belongs to the known terms. We shall shift to the right hand side. So we can write here plus c square into summation from j equals to 1 to n d psi ie dx d psi je dx dx uje equals to boundary integral along gamma e psi ie c square du dx d gamma e minus summation b belongs to eta g psi ie psi be integration along omega e dx d2 ube dt minus c square summation over b belongs to eta g integration over omega e d psi ie dx d psi be dx dx ube. Now integration over omega e psi ie psi je dx This is written as the mass matrix. We already have discussed it several times. So this is Mij. Then we have c square integration over omega e d psi I e dx d psi j e dx equals to Cij. Then integration over omega e psi I e psi b e dx equals to MIBE, and integration along omega e d psi I e dx d psi b e dx we can write it as K IBE. Here this should be del T2. Similarly here also this should be dt2. In the second order wave equation, there is no convection term. The right hand side term is treated as the diffusion term, though c square is not a diffusion coefficient, but because of the Laplacian operator on the right hand side, we treat the c square del 2u del x2 term as a diffusion term, and accordingly we change the symbol of the matrix from convection to diffusion matrix. So we shall define it as Kije. So this is Kije. The semi-discrete form can be written in a compact way as summation of j equals to 1 to nen Mij d2 uj dt2 plus summation j equals to 1 to nen Cij uj equals to boundary integral over gamma e w c square du dx d gamma e minus summation over b belongs to eta g m ibe d ube dt minus summation over b belongs to eta g k ibe ube. So this entire portion in the right hand side we can represent it by the symbol FIE. This is the ith semi-discrete equation. So we can write it in a compact way as summation over j equals to 1 to nen Mij d2 uj dt2 plus summation j equals to 1 to nen Cij uj equals to Fie. This is the compact semi-discrete form. Compact semi-discrete form, which after assembly can be written as, after assembly it may be written as m d2 u dt2 plus c u equals to f. So this is consistent mass matrix. This is global convection matrix. This is the DOF vector and the right hand side is the load vector after assembly. So we can use Newmark's method for time integration. The time integration of D2U dt2 can be performed by using Newmark's method. So here the convection matrix will be replaced by the diffusion matrix. So this is Kij, the EBC due to unsteady boundary condition. This should be D2UB dt2. Similarly, this should be Kij, and here this is the diffusion matrix. Okay, so this is global diffusion matrix. Now the second order wave equation, del 2u del t2 equals to c square del 2u del x2. Here the left hand side is the unsteady term and the right hand side is the diffusion term. In second order wave equation, there is no convection term and accordingly we don't have a convection matrix. Though c square is not a diffusion coefficient owing to the presence of the Laplacian operator, the c square del 2u del x2 term is considered as a diffusion term. We have shown that the convection matrix after assembly for quadratic bar elements is skew symmetric, similar to that noted for two-noded bar elements. We have presented the semi-discrete form of the second order wave equation, which is a hyperbolic partial differential equation. For today's class, I recommend the texts by Professor T.J.R. Hughes and Professor J.N. Reddy. Thanks a lot for your attention.